Okay, hello. This is ACM ICPC Training 39. This one we look at the question section 2.2 for party lamps. All right, let's take a look with the question. All right. Sorry. All right, party lamps. To brighten up the gala dinner of the IOI 98, we have a set of N, the lamps, colored lamps number from 1 to N. So maximum is 100. The lamps are connected to 4 buttons. Button 1, when this button is pressed, all the lamps change their state. Those that are on are turned off, and those are off turn on. So you can imagine. Button 2, change the state of all the odd number lamps. Button 3, change the state of even number lamps. And button 4 changes the state of lamps whose number transform 3 times k plus 1. So it's 1, 4, 7, 10, 30 and stuff. A counter C records the total number of button presses. So you have a limited number of presses. When the party starts, all the lamps are on, and the counter C is set to 0. Well, counter C is set to 0, but you need to input the counter C. You are given a value of counter C, and final state of some of the lamp after some operation have been executed. Write a program to determine all the possible final configurations, all the possible final configurations of the N lamps that are consistent with the given information without repetition. Yes. You are having 4 lines. The first one is number of lamps. The second one is the final value of C. That means if it's 1, you can press once, 2 twice, 3 times. And the line 3 is some lamps number on in a. So now it's -1. That means and spread by speed and space and terminate by the integer -1. So you will know -1 is if it's only -1, so it means nobody has to be on. But the line 4 is some lines number off in the final configuration. So in this case, the 7 has to be off. Okay. So output formats is lines with all possible final configuration without repetitions of all lamps. Each line has n characters, where the first character represents the state of lamp 1 and last character represents the state of n. And 0 means it's off, 1 means it's on. The line must be ordered from least to largest, so it's ordered. If there's no possible configuration, then you just need to print out impossible. All right. So in this case, you can see only 7s. This value, this value, this value. Only 7s are off. So you can push the button 1 and then turn off. You get this. And if you push the button 2, then you get this one. If you push the button 4, you get this one. And that is almost it about the question. Okay. Firstly, we need to establish some very simple rules. For example, the C here is 1, 2, 3, 4, 5. 5, so it's 10,000. If it's 10,000, then it's no meaning for us. If it's 10,000, we need to find out if it's a complete search. And definitely this is a complete search. However, any complete search, BFS, DFS, cannot be, and with 100 nodes, it cannot, with the 4 nodes, if in this way, we cannot really have anything as deep as that. So we must actually figure out what is the base state. Okay, you will notice for each button, if it's pressed twice, that means it doesn't really press, right? So actually we start to emulate every possible every duplicate presses which not taking any effect. So for example, if button 1 press 5 times, that is only as same as press 1 time. If button 2 is pressed 6 times, it's just as same as not pressing button 2. So we decrease them first by 2. So we decrease. Finally, the C falling into 0 to 4. 0 to 4, that means each of the button can only be pressed once, maximum, because if it's pressed more than once, it just means nothing. All right, so let's take a look with the code. A second, give me a second. Okay, lamps. All right. First, we enter N, the number of lamps. We have a C. All right. C is the number of pressed, and then we enter the lamps have to be on. So if it's not a -1, we just A count equals to N. We're just recording it down, and the same as the 1 has to be off. And then if C larger than 4, we reduce this to his base condition. So I have to make a range from 0 to 4, so my search depth is not going to exceed 4. And if C is 0, that means nobody is actually taking anything. That means all lights is on. So either is okay. I check either is okay. Other than in another case, it's impossible. Else, if it's not, means some button is definitely pressed. Then, if C equals to 0, this C is recording down how many cases I have ever searched. So if I haven't searched any valid results, then I see out the impossible. And if it is, I just additionally, R is the one who store the results. I sort it so it can be increased, be the increasing order, and then I just simply print out the results. And the whole DFS is just to search. DFS starts with 0, means nothing is pressed. Before we go to the DFS, I need to show you about all these existing functions. First of all is change. Remember, in this program, because I don't want to initialize it anymore, so I take it false is on and true is off. It's a little bit weird, but it's okay. So if it's off, then I turn it on. If it's on, I turn it off. This is a change the value of this L, the lamp's state. The optional one is to change every lamps. Option 2 is change the odd number lamps like this. Option 3 is changing even number, and option 4 is changing finally the 3 times k plus 1. Okay, and then the check. Check is check every for the final state. Check every lamps which if it's inside any in any list. For example, if it's in the list of A, that means this lamp has to be on. So if LAN is equal to lamp is in the list but is off, then I return a check as false. That means it's not a valid case, and then I just n++, so I can go through this while loop. And the same thing as Bn. If the lamp n is in the list of B, that means he has to be off, and turns out it's on. I also need to make the check to be false, and then so on and so forth. And finally, if I all pass, I return true. And the print is trying to construct a string. The string has to be empty at first and goes through 1 to n. If it's true, that means it's off. So I just plus a 0 afterward, and if it's 1, I just plus a 1 afterward, and then I return this as t. This is the one. The DFS, yes, DFS intuition is very easy. If because DFS n, the n means the number of time is pressed. So if n equal to c, then I check. If check is valid, then I call this string, and I want to know if it's the repetition of with my old strings. If it's not, then I record it, and then I C++, and that's it. And if I didn't reach to my searching, for example, if I have if my C is 3 but my N is only 1, I need to still searching on. I need to search the off word state. So if I equals to 1, I just change I option 1, and then I DFS N plus 1. And remember, this is not to find only one solution, but a complete solution. So after DFS, you need to recover it. So and so on and so forth is for second one, for third one, for fourth one, and then you can generate all the solutions. The test case is pretty small if we consider the depth is only 4, so we're doing maximum around 100 cases we need to search for, so it's pretty small. Let's try to turn it. In. See if it's cool. Yes, and you can see because we have a very small cases to search on, so the time is actually not a really big deal. I guess that is almost about this question. You need to search. You need to do a DFS. It's a complete search. Nothing more about it. Thank you. I will see you next time.